Welcome back. I'm going to show you how to represent some common surfaces as parametric surfaces using vector functions. We did something similar with parametric curves, where we learned how to represent a line segment or a line or a circular arc or a curve with the function y equals f of x or x equals g of y using a vector function. So this is similar to that, except it's harder, but it's also more interesting. Now, the simplest type of surface, and it's an important kind of surface, is where z is a function of x and y, or maybe y is a function of x and z, and so forth. And here, x goes from one number to another, and so does y. So we have a rectangle in the xy plane and a surface above it or maybe below it. So that there's a domain in the xy plane. I'll draw the actual surface above it. And I'll write parametric equations first. What I like to do is just let x equal u, y equals v. And since z equals f of xy, z equals f of uv. Now those are parametric equations. What we really want is a vector function, because it's easier to write, shorter to write that way, and we can also use vector operations. And to do that, we just put the component functions into a vector. Okay, and we need the domain. Since x goes from a to b, u goes from a to b. Since y goes from c to d and y equals v, v goes from c to d. And then there we have it. Now, the reason that I'm using u and v and creating new variables is that we have a couple formulas we're going to use, and I find them easier to use if I always use u and v. But you don't have to. You can use any letters you want. And sometimes people don't bother defining u and v. Sometimes people just call them x and y in there, but I prefer to always use u and v. I'm more comfortable with that. Of course, we could have, there's nothing special about z compared to x and y. We could have y being a function of x and z, and the roles of the variables are just switched. Behold the miracle of cut and paste. Okay, so we could have z being a function of x and y. Y being a function of x and z. And x could go from a to b. And z goes from c to d. That picture is going to be totally different. So let's get rid of everything except the axes. Okay, so x goes from a to b, y goes from c to d, z goes from c to d. So the domain is a rectangle in the XZ plane. It's not part of the surface, so I'm not going to sketch it very darkly. I'll draw the surface to the right. So our surface might look something like that. So this time I'll let X and Z be U and V respectively. And if Y is f of xz, that means Y is f of uv. And to make a vector function, I just put the three component functions into a vector, like so. And U goes from A to B. V goes from C to D. I'll do some specific examples in a minute. And of course, you can do something similar if X is a function of Y and Z. But I don't think it's worth writing it down. So I'll just say it's similar. Now, some surfaces can be represented in more than one of these forms. So let's take the example XYZ, where Z is so XY squared. X is between 0 and 2. And Y is between 0 and 1. Now, you don't really need to graph this to do the problem, but I'll attempt it anyway to help you see what's happening. So X goes from 0 to 2. Y goes from 0 to 1. The function is always non-negative. It's 0 on the X and Y axes. Otherwise, it's positive. So oops. Oh, this is terrible. Okay. So it might look something like that. I'll write the parametric equations first. You don't have to do that, but sometimes it helps to break it up into those steps. And then the vector function, X equal U, Y equals V. Since X goes from 0 to 2, U goes from 0 to 2. Since Y goes from 0 to 1, V goes from 0 to 1, and that's it. And you can give that vector function a name if you want. It would have to have a vector symbol, but you don't even have to bother giving it a name. Well, now I'll do an example where Y is a function of X and Z. So it's kind of similar to the previous example. So Y equals XZ, where X goes from 0 to 1, and Z goes from 0 to 3. I don't need to sketch that desperately to do the problem, but I'll make one anyway. See, X goes from 0 to 1, Z goes from 0 to 3. If X or Z is 0, then Y is 0. Otherwise, Y is positive. This is going to look vaguely like that. I'll draw the grid lines in different colors. Make them blue and green. So the blue lines are lines along which X is constant, and X is going to be U. And the green lines are lines along which V is constant, and V is going to be equal to Z. So since Y is XZ, Y is UV, those are parametric equations. I don't have to, but I'll give the vector function a name this time. R of UV is UVV. U goes from 0 to 1. The V goes from 0 to 3. Okay. So of course, not every surface has this form. Another important kind of surface is a cylinder. And for a cylinder, you should use cosines and sines. And the angle should be one of the variables. For a cylinder, the radius is constant, so it's not polar coordinates. But you should use cosines and sines for one of the variables. Here's an example. The half cylinder, x squared plus z squared equals 4. X is non-negative. Y is between 0 and 3. Well, a sketch actually is kind of helpful this time. So the circle has radius 2. It wraps around the y-axis, but we want the front half, and y only goes from 0 to 3. Oops. So the right halves of these circles are actually the back. Oh no, wait a minute. They shouldn't be there at all. Sorry. This is a half cylinder. My bad. Oops. You know what? Let me do something a little different here. I'm gonna make the um, those cross sections a different color. So that's our surface. I'm going to draw from another angle. I'll draw it from the left. And this can often be helpful if you just want to concentrate on like two variables instead of three. So from the left, I see X going to the right and Z going up. And I'm looking at the back of the Y-axis. And what I see is, from this viewpoint, the surface looks like a half circle. Of radius 2. So I'm going to write parametric equations first, which is a good intermediate step often. So X and Z go around in a half circle. Radius is 2. I'm going to call the angle V. You can call it theta if you want, but I like to stick with U and V because the formulas are more familiar that we'll use later. And the angle V goes from minus pi over 2 to pi over 2. Now this part can be a little tricky the first couple of times you do it. So y can be between 0 and 3. And y doesn't depend on x or z at all. So I'll just set y equal to the other parameter, u. If you want, you can just call it y, but I like to stick with u and v. So those are parametric equations. I'll make a vector out of them. Get r u v equals 2 cosine v u 2 sine v. And I've got the domain. The domain is an important part of the function. You can't skip the domain. Now, the reason that I use different colors here is I want to show you what the domain in the xy plane and what this function is doing. I mean the UV plane. So okay, so u goes from 0 to 3. V goes from minus pi over 2 to pi over 2. I'm afraid I got to make that longer. Because pi is about 3, so let's extend that u-axis. So the green lines are the lines where the angle is constant and the angle is v. Draw some grid lines of constant v, and the blue lines are the lines where y is constant. So that means u is constant. So those are vertical lines. Draw some of those grid lines. So the blue grid lines get sent to the blue arcs on the surface, and the green grid lines get sent to the green line segments on the surface. And every rectangular patch on the left gets sent to a cylindrical patch on the right. And the next time we're going to be concerned with the areas of these patches. Now, the areas of the patches on the right, in general, are different from the areas on the left. And they're usually different from each other. In this problem, all the patches on the right should have the same area, but they're all double the area of the boxes on the left. Next, I'll introduce another kind of surface. This is a surface where z equals f of xy, and xy are inside a, I should say, inside a disk. And what you should do then is use polar coordinates for x and y. And again, you can use r as theta if you want. I prefer to stick with u and v because we'll have some formulas later that will just look weird if we used r and theta. So here's an example. The set of points where z equals x squared plus y squared, and z is less than or equal to 4. Well, this is our old friend, the elliptic hyperboloid, or bowl. If we project this surface down to the xy plane, what we would see is a disk. I'll make the horizontal traces green and the vertical traces blue. So Let's look at the shadow of this surface on the XY plane. That's a disk. So we need to find the radius of the disk. Sorry, that should be 4, not 2. Well, along the rim of the vase, z equals 4, and z also equals x squared plus y squared. So the radius is 2. If I looked at this from above, if I look at it from above, what I see is a disk. Well, it's not quite, that should be a circle, but I see green concentric circles and spokes, blue spokes that go through the origin. Yikes. Okay. And the radius is 2. So I'll represent x and y using polar. I'll let v be the angle. You could let u be the angle if you want, but it doesn't matter. The radius u goes from 0 to 2, and the angle v goes all the way around in a circle. So v goes from 0 to 2 pi. V is x squared plus y squared. And by the magic of trigonometry, that simplifies to u squared. Once I have parametric equations, I can make a vector out of them. I get u cosine d, u sine d, u squared. And there it is. Now, if I think about the areas this time, which we'll do next class, these patches don't all have the same area. Unlike the previous example, the patches on the surface, the ones that are higher are bigger. And one thing we'll have to figure out is exactly how big they are. We'll learn how to do that. Well, you can do the same thing with polar coordinates, and sometimes you should. If y is a function of x or z, x and z, or x is a function of y and z, and so forth. So let's take a look at that, and an example of that. Suppose x is a function of y and z, and y and z are inside a disk. What we do then is we put y and z in polar coordinates. So suppose x is a function of y and z, and the y and z are inside a disk. So here's an example. The part of the plane z equals 4 minus x minus 2y. That's inside the cylinder Y squared plus Z squared equals 4. Now, wait a minute, you say. I thought X is a function of Y and Z. Here, Z is a function of Y and X. But well, we can take that surface and solve it for X. But we'll have to do that. So a sketch is helpful. This cylinder has radius 2, and it wraps around the x-axis. And we want the part of a plane that's inside that cylinder. So this is a flat surface. It's not a cylindrical surface. It's part of a plane that's inside a cylinder. See, the plane has intercepts 4, 2, and 4, I guess. And the part that's inside the cylinder is a, I guess, a solid ellipse, you call it. Not a great sketch, sorry. It doesn't need to be great, though. So this is a filled in tilted ellipse. It might help to draw it from a different point of view from the front. If I look at it from the front, what I see is a disc. And a disc is a lot simpler than this filled in ellipse. So this is a view from the front. What I see is what I see from the front is a disc. A disc of radius 2. So I'll use polar coordinates for X and Y. The radius is U, which goes from 0 to 2. The angle goes in a complete circle. So B goes from 0 to 2 pi. Now for the X, I need to solve the plane equation for X. And when you do that, you get X equals 4 minus 2y minus z, which is 4 minus 2u cosine b minus u sine b. So now I have parametric equations. I'll make a vector out of them. Okay, R of UV is 4 minus 2u cosine b, oops, sorry, minus u sine b, comma, u cosine b, u sine b. This, and I already found the domain. This is not the only correct answer. These problems always have lots and lots of correct answers. Try that again. Ta-da. I think this is enough for now. And next time we'll start doing calculus with surfaces. Bye-bye.